Good morning, everyone. Welcome to Knowledge Hub by Sri Chaitanya. I, Harish Sen, Senior Physics Faculty, welcomes you to another PPT or let's say lecture of Vernier Caliper. Today we are going to study about Vernier Caliper. So what is a Vernier Caliper? Vernier Caliper is an instrument. It is a measuring instrument which we use. It is used to measure the length of objects, okay, and it measures the length of the object very precisely. So let's see what are the terms involved in it, and from the perspective of JEE mains and advanced, it is a very important question or a topic. So let's begin. So Vernier caliper. So Vernier caliper is a precision instrument, right? So as I say, it precisely measures anything. So it is a precision instrument that can be used to measure internal and external distances extremely, okay, accurately, right? So what does that mean? So let's say if I have a ball, yes, if I have a ball, and if I want to measure the diameter of the ball, right? So what will I do? So with a scale, can I measure the diameter of the ball? So let's say this is a ball, and I will use a scale to measure the diameter of the ball, right? But in this is a circle, if you see correctly, right? So for a circle, it is easy to measure using a scale. But for a 3D object, you see, it will be a round sphere. So I cannot accurately measure using a scale. It will be very difficult for me. But with the help of Vernier caliper, we will see that it is very easy for us to find the radius or the diameter. The accuracy obtained in measurements using a meter is up to 1 mm, right? So using a Vernier caliper, what is the accuracy which we get is 1 mm. What do you mean by that? So let's take an example that I have a 15 centimeter scale, right? So what does a 15 centimeter scale look like? A 15 centimeter scale look like something like this, right? Where I have a scale and there are marks from 0 to 1 to 2, 3 until 15, right? And if you look between 2 to 3, between any numbers, how many divisions more you have? You have 10 more divisions. So this is 2, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9 and 3. Right? And what is the minimum that I can measure? The minimum I can measure is this much. This is the minimum length I can measure, right? And this minimum length is what? So if this total is 1 centimeter, if the total is 1 centimeter, this one block is of length how much? Can I say it is of 0.1 centimeter? Because if I add 0.1, 0.1, 0.1, 10 times, it will become 1 centimeter. So what is the minimum I can measure? Minimum I can measure is 0.1 centimeter. Yes. So here we is saying that what is the accurately I can measure with a Vernier caliper. With a Vernier caliper, I can accurately measure up to 1 mm. So we will see that also, that how you can measure that. Okay, but it is not hard and fast that it should be 1 mm only. Okay, it will depend upon the instrument. It will depend upon the instrument, and that is basically the least count of the instrument. Least count means least how much I can count with that using that instrument. Okay, so it depends on the instrument. It is not hard and fast that it should be 1 mm, but for most of the Vernier calipers, it is 1 mm. A Vernier caliper consists of two jaws. One is a fixed jaw with main scale attached to it, okay, and the main scale has a centimeter and a millimeter marks on it. So Vernier caliper is made up of two scales. One is a main scale, another is a secondary scale. So this main scale is like a normal 15 centimeter scale which you have, with main divisions are in centimeters and it is divided into small parts. The other jaw is a movable jaw, so the other secondary scale is basically movable. Vernier scale has 10 divisions over it, so that each of the division is 0.9 mm. Okay, so let's understand that later. Okay, let's skip this sentence for now. So now let's first look at the figure, that how does a Vernier caliper actually look like. Okay, so if you have done some experiments in your lab, okay, in your class 11th lab, you might have seen this type of instrument. Okay, so what is this? This is typical representation of a Vernier caliper. So what do you have here? Let's look here. So see, if you look closely, this is at the scale. Okay, if you look closely at the scale, this is basically the vernier scale. Sorry, this is the main scale. Okay, this is my main scale. So let's write this, that what is your main scale? This is my main scale. What is this? This is the secondary scale, or I can either use this also as the secondary scale. So now what are this? These are the external jaws, these are the internal jaws. So if you look here, so let's say this is my movable scale, okay, movable scale. So now what is this basically? Okay, so now this is this is where I keep. So let's say if I want to measure the radius of a ball, I will keep my ball like this, right? So now what I'll do, I'll fix my ball here. Okay, I can move this using this slider, this can move forward, this can move backward. So I will fix my object here to measure if the object, whatever object I want to measure. And with the help of two scales, that is the main scale and the vernier scale, I will be getting the exact reading. Okay, so this is the basic representation which you should know, and we'll understand it more that what that does that represent. But like you might have one doubt that why do we need this scale, right? What is the problem with the main the normal scale which we have, 15 centimeter scale? Let's understand that. So let's say if I have the scale, 15 centimeter scale, this is 0, this is 1, this is 2, this is 3. Okay, and it is still 15. So this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9 and 2. Yes. Now let's suppose if I want to measure the length of this pen. Okay, if I want to measure the length of this pen. So what I'll do, I'll keep a pen, my pen like this, right? And I'll try to measure the length. So let's see. This 0 coincides with this 0. And this 1 is somewhere here, right? So now what is the length? So you will say this length is 1.1, 1.2, 1.3 and 1.4. So my length is somewhere between 1.3 and 1.4. Yes. But do I know the second digit? No. Okay. What is it? Is it 1.35? Is it 1.36? Is it 1.34? Yes. What is the second digit? We want to know. We want to know that, right? But with this instrument, can I measure the second digit? No, I cannot measure the second decimal point. So what if I have an instrument which maximizes this? Okay, which magnifies this. So this point distance, this 0.1 centimeter, that is the distance from 1.3 to 1.4. If I can magnify that, into 10 equal parts, so this is 1.3, this is 1.4, and again 10 divisions, right? So now what will happen? The nib of the pen will be coinciding, let's say somewhere here. Let's say it's coinciding somewhere here. Then what can I say? This is 1.3, 1.31, 1.32, 1.33, 1.34, 1.35. Yes, so 1.35 is the answer. Yes, so I can get the second digit if I can, what can I do? If I can magnify this. Similarly, what is happening here, that this movable scale or the vernier scale is basically magnifying the main scale. Okay, you should understand this. Let's move. So now let's talk about some terms which are used for the vernier scale. So first is least count. Okay, so let's understand what a least count is. The difference between one scale division on main scale and one vernier scale division is 0.1 mm. Okay, it is called least count. Okay, so now it is not hard and fast, it is 0.1 mm, but usually it is 0.1 mm. Okay, so let's understand what is this. So if, let's take this as my main scale. This is my main scale. This is 0, this is 1, this is 2. Yes, and I have division, so 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9 and 2. Yes, so what is one main scale division? One main scale division is basically the reading of one division on my main scale, one division on my main scale, one division on my main scale. So these small divisions on my main scale, okay, so this reading of this one division, this is one division, or I can say one main scale division. Similarly, I will have a 1 year scale also like this, right? I will have a 1 year scale also. So let's say this is my 1 year scale, and similarly from 1 year scale also 0 to 10 I will have divisions. So the reading of one division on my main scale, the reading of one division on my main scale, okay, this is one division on here, just 1 minute, this is one division on main scale, on 1 year scale, okay. So one division on 1 year scale, okay, one division on 1 year scale is basically my 1 VSD. Okay, so what is least count? So the formula for least count is given as, so let's write the formula. So the least count is basically 1 main scale division minus 1 Vernier scale division. Okay, so this is the formula which you should remember. Now, there is one more formula, and that formula is least count of Vernier, smallest reading on main scale. Okay, so let's first look at the main scale and the Vernier scale. Okay, so let's say, let's take this as an example. Just 1 minute. Okay, so let's take this as an example. Okay, so now if I take this as an example, what can I see? I can see that, what is the formula? Smallest reading on main scale. So what is my main scale? This is my main scale, right? And what is the smallest I can measure using my main scale? So main scale is basically my 15 centimeter scale, and with that the smallest I can measure is 0.1 centimeter. Yes, so this is basically 0.1 centimeter or 1 mm. Upon total number of divisions on 1 year scale. So let's say if I have 10 divisions on my 1 year scale, I will divide it by 10 total divisions. Okay, total divisions, I will count the divisions, 1, 2, 3, 4, like this. I will count the divisions and see that I will have 10 divisions here. Okay, so this is the second formula where smallest reading is basically 0.1 centimeter, 0.1 centimeter, that is basically 1 mm upon total number of divisions on the secondary scale or the 1 year scale. So from here I will get 0.1 mm. Okay, so that is why they are referring as 0.1, because 0.1 is basically generally the 1 year caliper least count. So there are two formulas. I hope you understand both the formulas. So this formula is 1 MSD minus 1 VSD, and this is smallest reading on main scale upon total divisions on main scale. Let's move forward. So what is the working of a 1 year caliper? Let's talk about the working of a 1 year caliper. The sliding jaws run on the main scale with the guiding surface, which is accompanied by a 1 year scale in which it has a measuring tip on the left side. When two measuring tip surfaces are in contact with each other, the scale shows 0 reading. Okay, so what he is trying to say in the first two lines, that with the help of this I am able to move it forward and backward, right? But when there is nothing to measure, okay, when there is nothing to measure, what will happen? That my division, okay, so this slider which I have here will be somewhere here on 0. Okay, what will happen? That this 0 will coincide with this 0. Let's look at other diagram. That this 0 will coincide with this 0. Okay, when I'm measuring that, this 0 will coincide with this 0 because I don't have anything to measure, right? So if I don't have anything to measure, the reading should be 0. Okay. Now, let's talk about the third sentence. The final adjustment of the movable scale can be done by adjusting screw. So now if I have an adjusting screw also, okay, with the help of that, if I turn my adjusting this screw, okay, what will happen? This scale will move, this scale will move forward, this scale will move forward, okay, by a very small distance. First, the whole movable jaw assembly is adjusted so that the two measuring tips just touch the part to be measured. Then lock B is tightened. Okay, so first I'll fit the object inside it, and with the help of adjusting screw, I'll try to find the distance. Okay, final adjustment depending upon the sense of correct feeling is made by adjusting screw, which makes the part contain locking nut A and sliding jaw to move as the adjusting screw rotates on a screw which is in a way fixed to the movable jaw. After all the final adjustment has been done, the locking nuts has been tightened and the reading has been noted. Measuring tips are designed so that they can be used to measure external dimensions as well as internal dimensions. Okay, so first of all, what he is trying to say that just put your object here with the help of this screw, just tighten it here so that we can measure the reading, and with the help of the scales here we measure the reading. Okay, so this is what he is trying to say. Now, so there are two types of errors now. Okay, with whatever you measure, there are some errors, as we studied in the last chapter, that is units and dimension. There are errors, right? So now we also have some errors here, right? If I take a reading, I will have an error. So zero error. So what is zero error or zero correction? First of all, find the error in any in the measuring instrument. It is called a zero error. So I'll give you an example. Let's suppose if I want to measure my weight, let's say my weight is 75 kgs, and if I stand on a weighing machine, yes, and let's suppose before getting onto the weighing machine, the weighing machine is showing 1 kg. So when I will stand on the weighing machine, what will it show? It will show 75 plus 1, that is 76. Yes, because my weight is 75 and initially it was showing 1 kg. So when I will stand on it, it will show 76 kgs. Yes, let's say if instead of plus 1 it was showing minus 1. Then if it was showing minus 1, then when I get onto the weighing machine, what will be the reading of the weighing machine? It will be 74 kgs, right? Because 75 minus 1 is 74 kgs. Okay, so if it has, so if the reading of the weighing machine before measuring something is plus 1 kg, then I will say it is a positive error. Similarly, if the reading is negative before measuring anything, then it will be a negative error. So there are two types of zero errors, a positive error and a negative error. So let's understand this. So knowing that the zero error, necessary correction can be made to find the correct measurements. Yes. So if I knew that the reading is, the weighing machine is showing plus 1 kg extra. Yes. So what can I do later on? I can, so let's say when I stand on it, it will show 76 kg. So I can subtract minus 1 from that to get my actual reading. So that is what he is trying to say. Such a correction is called zero correction. Zero correction is the negative of zero error. Okay, so zero correction is the negative of zero error. So let's understand here. So to find the zero error, close the jaws of a vernier caliper gently. So what I'll do, I'll close the jaws. Okay, so what will happen, that these two jaws will now be in contact because I'm measuring nothing. So what should ideally happen, that this 0 and the 0 of my vernier caliper should both coincide. Yes, this 0 shall coincide with this 0. Yes, to find the zero error, close the jaws of the vernier caliper gently. If zero line of the vernier caliper coincides with the 0 of the main scale, then zero error is 0. Simply, right? That is, if this line coincides with this line, then I'll say there is no error. Correct? If before measuring anything, if I take my instrument out, weighing machine out, and it is showing 0 kgs, then there is no error in the weighing machine. Now, zero error will exist if zero line of the vernier scale is not coinciding with the main scale. So if you can see here that this 0 of the main vernier scale and the 0 of the main scale are both not coinciding. Yes, so now I know that I have some error. Okay, when there is no object here and the two jaws are in contact, this 0 should coincide with this 0. But if it is not coinciding, I will say that I have some error. Okay, and now 0 error is now 0.07 is, so now let's understand this. So if it is forward, I'll say I'll have a positive error, right? Because it is in forward of 0 and it is measuring something. If this 0 was behind, it would have been a negative error because it's like -1 kg. So let's first of all, to find it the error is positive or negative, we have to first understand that how to measure the readings. Okay, how to take the readings. So let us find the diameter of a material using vernier caliper. Okay, place the material between the jaws of the vernier caliper, close the jaws till they press the opposite sides of the object gently. So I will keep my object here, right, and it is pressing the object from both the sides. Note the complete divisions of main scale past the vernier scale 0 in a tabular form. So let's understand what he's trying to say. So first of all, just 1 minute. So let's make a diagram here. Okay, let's try to make a diagram here. So first of all, just 1 minute. Okay. Okay, so let's take an example here. Okay, so if you can see that first, okay, let's forget about the 0 error. Okay, there is some error here. Okay, because this 0 is not coinciding with the 0, so there is some error, 0 error. But let's forget about that error right now. Let's see how to take the reading. So first of all, I'll find that where the 0 of the vernier caliper is. So if you see that the 0 of the vernier caliper is at this point. Yes, so let's make this diagram, that this is my main scale. No, it will not help you. The 0 of the vernier caliper is here, right? And I'll see that where it is. So this is my 0 of the vernier caliper. And if you look on the main scale, this is my main scale. So where is the 0 of the vernier caliper? So the 0 of the vernier caliper is between this point and this point. So what is this point? This is 10, 11, 12, 13. So you can see, if you can see that this is 10, this is 11, this is 12, and this is 13. So this is my main scale. This is my main scale, this is my vernier scale, right? My vernier scale is something like this. Okay, so if you see that my main scale, this is my main scale, this is my vernier scale. So where is the 0 of my vernier caliper? The 0 of my vernier caliper is between this point and this point. So what is this point? This is 10, this is 10.1. No, this is basically 10, 11, 12. Okay, so this is basically 11, 12, 13. Yes. So I know that the reading is greater than 12 but less than 13. So the reading should be between 12 and 13. Yes. So what is the main scale reading? So main scale reading will always be the smallest one. So that is 12. Plus I'll write least count of the scale, whatever the least count of the scale is, into. Now second step, listen very closely. I'll see that which line from my vernier scale coincides with which line on my main scale. Okay, so basically I'll find the line which is coinciding. Now forget about everything and just tell me that which line is coinciding with the line above. Yes, so if you see very closely that this line is coinciding with the above line. Yes, this line is coinciding with the above line. So just find that which line is coinciding. So let's count. So this is 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8 line is coinciding. So just write it here. To find this, I will just find that which line is coinciding. So what the formula becomes? The formula becomes actual reading is basically main scale reading plus least count into Vernier scale reading. Okay, this is the formula, and please remember this. Very important formula. Least count, I already told you there are two ways. Main scale reading is how you find that where is the zero of the Vernier scale. So zero of the Vernier scale is between 12 and 13. So just take the small reading. And how to find the 8, that is the Vernier scale reading? Just find that where the line is coinciding with the above line. That number of line is basically my Vernier scale reading. Okay. So now, so what is happening here? So same thing we are doing here. Okay. Same thing we are doing here. So multiply it by the least count. So let's note the complete divisions of main scale. Find the Vernier scale 0 in a tabular form. Next, find the Vernier scale divisions that is coinciding with any division on the main scale. Right? Same thing which I told you, that I have to find that which is coinciding. Okay, if you look which is coinciding, next find that Vernier scale division that is coinciding with any division on the main scale. Multiply it by the least count of the Vernier caliper and add it in the main scale reading. This is the diameter of the material. Okay. Add zero correction to get zero measurement. Repeat the above procedure and record observations. Okay, so same thing. So whatever error I have, so this is the way I can find my readings. This is how I am finding the reading, and finally I'll subtract the error. So what are the disadvantages? So advantages, it is accurate, integrate scales. Okay, integrated means there are two scales in one. Versatile, because I can measure the length of the, let's say, a cylinder, diameter of a cylinder, diameter of a sphere. Okay, so it is very versatile. It is durable and it is cost efficient. Disadvantage is that I need a very good eyesight, because I want to find that which division is coinciding with division. Yes, so a very good eyesight is required, and knowledge of Vernier caliper is required, because if I don't know how to use the Vernier caliper, I'll not be able to get the readings, right? A normal scale everyone can use. You are not taught in a school that how to use a scale, but the Vernier caliper you require knowledge. Possibility of errors, because if let's say I find that I'm not able to correctly identify that which is coinciding, then there will be some error. More accurate tools available. Okay, there are more accurate tools available than this, and one of them is screw gauge, which will be seen in the next class. So okay, I have a quick quiz for you. So what is the least count of the Vernier caliper? The least count of the Vernier caliper is 0.1 mm or 0.01 centimeter, or I can say 1 main scale division minus 1 Vernier scale division. What is the range of Vernier caliper used in a physics lab? So that is, okay, so now this is basically in a lab a 12 centimeter. Okay, how many divisions are there in a Vernier scale? So 0.9. What is the zero correction? So zero correction is the error which we have, okay, before measuring anything. So let's do this question. So this is basically a screw gauge question. Let's do this question. Find the zero error. Okay, so let's find the zero error here. Okay, I'll help you to find the zero error. So first of all, zero error is basically similar thing. Okay, so let's first find the zero of the Vernier caliper. Zero of the Vernier caliper is between 0 and 0.1. Because this is 1, this is 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so zero error. So zero error is basically, let's see. So where is the main scale reading? Main scale reading is between 0 and 0.1. So I'll say 0 plus. Now, okay, what is the least count? So let's write. Let's say there is some least count into what is coinciding. So let's say if this first line coinciding, no. Second line, no. Third line, it is coinciding, no. Fourth line, no. Fifth line, it is coinciding. So I'll write 5. Yes. And the normal least count of a Vernier caliper is 0.1 mm. So 0.1 into 5. So this will give me plus 0.5 mm. So that is my zero error, plus 0.5 mm. So I hope it is now clear to you that how you can find least count. Least count is similar, okay, similar to how you find the reading, okay. It does that there is nothing to measure. If there is nothing to measure, what is the reading? That is basically the least count. Okay, and this question is there. So we have done the main part, right? We have done the main part. So the main scale reading is -1 mm when there is no object between the jaws. Okay, so he is saying that when there is no object between the jaws, so let's say zero error. So zero error. So zero error is basically main scale reading is -1 mm plus in the Vernier caliper 9 main scale divisions with matches with 10. So he is saying that 9 main scale divisions equals to 10 Vernier scale divisions. Yes. Assume that the edge of the Vernier scale of the as the zero of the Vernier, the thickness of the object used. Okay, so let's understand here. So what is this? This is basically a centimeter scale, right? So now I know that one main scale division is basically how much? 10 by 9 Vernier scale divisions. Okay, so now this is how you can find the least count. So I know that what is 1 means. So what is 1 VHD? 1 VHD is basically 9 MHD by 10. And what is 1 MHD? 1 MHD is basically 1 main scale division, that is 0.1 centimeter. So I will have 9 by 10 into 0.1 centimeter. So this is 0.09 centimeter. That is my least count. So this is my one Vernier scale division. So what is the least count? So least count is basically 1 MHD. 1 MHD is 0.1 centimeter minus 1 VHD is 0.09 centimeter. So this will give me 0.01 centimeter. Correct? So this is how I can find the least count. Just write the least count here. So that is 0.01 and this is in centimeters. Okay? Into this is in centimeters, this is in millimeters. Into which is coinciding. Okay, so before keeping anything, I can see that this fifth line is coinciding. So just write fifth. So you have a zero error now, you have a reading now. Okay, you have your main reading now. Just to try to find the answer. So I have just given you the hints for this question. You please try to answer this question and write the answers in the chat box. Okay, I'll just pin the correct answer. Okay, so I hope this session was very clear to you and you understood everything. Let's meet in the next class with screw watch. Okay, I will also please try to solve questions because solving questions will help you. And if you have any doubts, please join and ask me in the comment section. Thank you everyone.